guys become famous.
Welcome back to our YouTube channel.
Don't forget to subscribe.
Don't forget to hit the like button. Please support our channel. We're going big. Yeah. We'll buy you McDonald's.
To subscribe. Oh, we need a shout out for
We'll give you a shout out.
Sarai.
Oh yeah.
I don't know her YouTube channel. I forgot what she said. There's somebody else, but I can't remember. Yeah. Subscribe to whatever Sarai's YouTube channel is.
And shout out to all of our subscribers, you know.
If we reach 50 by the end of the week, we'll start posting the answers to tests.
So when you are
To chemistry,
calculating the
yeah.
wave
Yeah,
equation,
to chemistry test. We'll record.
you have
Nobody has to know.
to keep in mind this algebraic equation,
Yes, algebra.
expression, I mean.
My favorite.
All right?
Oh.
44 is equal to 6x. How do you find x?
Divided by 6.
Divide what?
Yeah, because it's giving me a
Sides,
headache.
right? 4 is equal to 8. Right? It's the same
Kelly bit my
concept.
homework.
What confuses people,
She ate it.
No, it didn't.
what confuses people is
Remember,
the
24
scientific
equals 6.
notation. I don't know.
What?
You
24
have to
equals
look
6.
at these numbers like they're
Where are
one
you writing
number.
that?
The only thing about it is, this is
What's it?
point 0.000006.
Yeah.
So instead of having to deal with all those zeros, we're just gonna use 6. So when you are multiplying with scientific notation, what happens to the exponents? When you multiply with scientific notation, you add the
You add
exponents. And so when you divide,
Subtract.
you subtract the exponents,
Oh, I'm
right?
so smart.
Okay, so when you set this up, you're just
Big
filling
brain.
in
Yeah.
the equation, plugging in. So what's C?
3.0 times 10a to the 8th power ms.
Okay, we say meters per
Meters
second,
per second.
but you write M/S. All right, so equal. What's next?
You got F equals
Wait,
Wait.
these are givens. We're looking for
I'm so smart. Doing my work.
So here's the equation. C is equal to wavelength times frequency. So what do I write after the equal sign?
6.0
I'm only doing. Ooh, I'm sorry.
6.0
This one has some.
times 10 to the
This one's like a little bit wrong because it started
next
right when I
7 meters
times
Line
times
ties. We're professional.
F.
She has a whole blazer.
Okay? We got that?
Yeah.
You plug in the values into your equation. Now, how do I find frequency? Divide what?
My blazer has the logo and everything.
What am I
Yes.
dividing?
What logo?
Okay, y'all remember this, right?
Why not?
It's branded.
Oh, you're dividing
It's
the
branded by
both
The
sides.
same thing. So I'm dividing both sides by 6.0.
Yeah.
Oh my God.
Oh, yeah. It's only 50.0.
2.0
You're so smart, Cindy.
I know, right? I know I'm smart.
And this
That's why
cancels
I'm
out, right?
famous.
All right,
So we're
so
both
what's the
famous.
answer?
I don't know. Collie.
3.0.
Leo, right?
Oh, there we go.
Don't say my name.
It's Collie. Yes, it's Collie. And what's your name?
Yes, it's 3.0.
It's a name.
What is it?
What's 3 divided by 6? 6 divided by
Ivy?
3 is 2. What's
Ivy, Collie.
0.2.
No,
Negative 2.
no.
Negative?
I hate this class.
3 divided by
I like
6
this class.
is what?
Yeah, you like it.
0.5.
0.5.
I told you.
0.5.
I got it right. 0.5 times 10 to the what? So you
Sam said he
subtract,
was
so you're
gonna
gonna
leave,
say 8
hate
minus
comments.
-7 is
22
equal to what?
views.
15.
Please comment on our videos.
Because
Yeah,
that turns
good
into a
comments.
positive, so you
Like,
end up
y'all are
adding
so smart.
Now, I
'Cause
want
we are
one
smart.
number in the ones place. Which way do I move my decimal?
You tell me, you're a teacher.
To the right.
Please
One
tell us what-
time. I'll
give
get
us
5
ideas.
times
Yeah,
10
give us
to
ideas
the.
for content.
Now, when I move my decimal to the right, what happens to my exponent?
It decreases.
It decreases by 1, so that becomes to the 14th power.
I knew that.
Oh my
I
god.
got the way. Lower.
You got it?
Should we tell him to
Is it on your
subscribe?
paper? On your note-taking guide?
No. Yes.
You should subscribe to us.
Just give me your name and I'll do it.
Okay.
Say it.
It's Professor Sandy.
On the accuracy of the equations that will be involved.
Peekaboo.
8 minus negative
Scared me, Cindy.
So those two negatives turn at 7.
Where was the wire?
Why or
Let
I?
me write it down.
Hurry up, Cindy. We're about to lose a subscriber.
Did you find it?
Are you struggling,
I'm
Cindy?
trying to fit asking me. Don't ask me. You too,
You
man.
shouldn't end it. Oh, I spelled that.
Give it to your friends. Tell them to subscribe.
Tell everyone to subscribe.
Tell your dog too.
Yeah.
Family, yeah.
Tell your grandma to subscribe. Why is that funny?
Nothing.
Come on, we gotta give it one star.
I just did it. I'll keep the page.
Yeah, give it out.
Just make little slips and like
That's what I
give it to
said.
random people.
That's what I said. Subscribe. Alright, let me do like subscribe.
Go faster, Cindy.
Osmo? Rosmigas? Osmo Rosmigas?
Get Cindy.
This is how you become famous. You work hard.
Yeah, you have to work very hard to become famous.
Also, you have to subscribe, so this is gonna pay Kelly and my college tuition.
Yeah, you're funding our education for us because we're poor.
We are, that's why we go to the school.
What
Which
school?
is named
What school?
Oh no! Okay, I'll blur that out. Yeah, what school?
We don't go to school. This is just a room,
Yeah,
right?
we're just like at a coffee shop. You know?
Yeah, at a
Watching
coffee
videos.
shop. It's just the coffee shop is just very loud, you know.
Yeah, with so many people. Look
Tell me
at that. That's how you become famous.
Yeah, just hand it to random people, you know,
Random people, you know.
on the street.
That was the bartender. That was the barista. The teacher here. That was the owner. The manager. Yeah.
Now, I don't know if you're talking about this part. Y'all just socialize. Now, can we conduct ourselves accordingly?
Yes, ma'am.
To the equation and solve. We know that the speed of light is a constant equal to 3 times 10 to the 8th meters per second.
Yeah, the owner got really good.
We also know that the wavelength of the wave is 6.0 times 10 to the negative 7th meters. Now, we solve for the frequency and find the answer to be 5.0 times 10 to the 14th hertz. Let's try one more. What is the wavelength of yellow light if the frequency of that color of light is 5.0 times 10 to the 14th hertz? The speed of light is a constant, so we know that c is 3.0 times 10 to the 8th meters per second. We have been given the frequency of the yellow light, So we simply plug the numbers into our wave equation and solve. Remember that the hertz simply means per second. Voila! The wavelength is 6.0 times 10 to the negative 7th meters. You'll have a chance.
Alright, so it's the same thing we just did, right?
It's the same thing we just did.
Except they were looking for wavelength instead of frequency. But it's the same setup. So the wavelength variable was here.
Yes.
But you still have to divide both sides to get the wavelength on the side by itself. And so you should get 6 times 10 to the negative 7. So when you divide it, 3 by 5, it was 0.6, right? 8 minus 14. Okay, negative what?
Negative 7.
6. And then when you moved your decimal to the right, what happened?
Goes down.
It decreased. You got it?
Yes, ma'am.
No.
Write the answer down and then go back and rework it. Make sure you can get that answer again.
Yes, after this program, to practice some of these problems yourself.
Yep.
Now, let's look at the particle description of light.
Max Planck could only explain the results of experiments he performed if he suggested that energy exists in small bundles or particles called
Write it down.
quanta. Planck proposed that a quantum of radiation is the minimum amount of energy that can be lost or gained by an atom. Planck also suggested that the energy of a quantum of radiation is equal to the frequency of the radiation emitted multiplied by a constant known as Planck's constant. From this equation, we can see that the energy of light is directly proportional to its frequency.
What is the modern view of light? How is this dilemma of light as a wave or a particle to be solved? Apparently,
Yeah, because I ain't supposed to be doing this anyway.
Let me do it.
What does E equal?
First of all, I said Lizette. That extra come
Lizette already did one.
Yeah, this is a good idea.
What does E equal?
She did such an amazing job the first time. I think she can do it.
Hey, Q, H, F. Pay attention, Cindy. Okay, sorry.
We can see that the energy of light is directly proportional to its frequency.
what is the modern view of light? How is this dilemma of light as a wave or a particle to be solved? Apparently, some experiments can only be explained if light is viewed as a wave, while others can only be explained if light is viewed as a particle. Our modern view of light is attributed to Albert Einstein, who in 1905 introduced the idea that light has a dual wave-particle nature. Although light has many wave-like characteristics, it can also be thought of as a stream of particles, or
Ashley, did you get a sheet? Oh, you did. Look at you.
It's, you go.
That's what smart people do.
Yeah.
That's what Cindy does.
It's all done.
Fire alarm.
quanta, which Einstein called photons. Modern scientists suggest that the nature of light depends on the experiment.
Boop. I scared her.
Let's examine the nature of light. Watch as the student performs flame tests. She places a small amount of a chemical on the nichrome loop and then burns the chemical at the flame of the Bunsen burner. Different chemicals will produce specifically colored flames. Copper compounds produce a blue flame. Sodium compounds produce a yellow flame. Strontium compounds produce a red flame.
Very cool.
A beautiful fireworks display is possible because of this very same concept of excited atoms that have absorbed energy, then given off visible light as they drop back down to the ground state. Just as in flame tests, in fireworks, barium compounds produce green light, sodium atoms produce yellow light, and compounds of strontium produce red fireworks. Fireplace logs or pine cones that burn various colors are another example of this phenomenon. Manufacturers simply treat the pine cones with certain chemicals so that a colorful fire will result. The light emitted by an element when its electrons return to a lower energy state can be viewed through an instrument called a spectroscope. A spectroscope works like a prism. If I look through this spectroscope at the flame produced during our flame test, or at a gas excited by electricity in a discharge tank, the light is separated into the various colors it contains.
The science of studying visible light through the use of a spectroscope is called spectroscopy. Each colored band of light represents the energy that is released by an electron when it returns from an excited energy state to a lower one. The energy of each band of colored light is equal to the difference between the original and final energy levels of the electron. These bands are called spectral lines and are the fingerprints of the element. Note two elements have the same set of spectral lines, just as no two people have the same fingerprints. We call this set of spectral lines the bright line spectrum of the element.
Today's modern picture of the atom still goes a step further than Bohr's energy levels. Like Bohr's model, the modern model of the atom predicts energy levels for electrons. But unlike Bohr's model, the modern picture of the atom doesn't describe the exact path an electron takes around the nucleus. Instead, it is concerned with the probability of finding an electron in a certain position.
Today, rather than having discrete bubbles defined within the atom, probabilities are now assigned to different areas surrounding the nucleus. This is called the charged cloud model. This model represents electrons as being part of a diffuse cloud, varying in density. The most dense areas showing the highest probability of finding an electron at any given time.
The word orbital has been chosen to describe the region of space around the nucleus in which an electron is most likely to be found. We can compare the orbital description for electrons with the pattern of holes in a dartboard. After a dartboard has been used a lot, there are lots of holes near the bullseye. Now, as we move away from the bullseye toward the edge, there aren't as many holes, but there are a few. These holes in the dartboard don't tell us about the order in which the holes were made, or even where the next dart will land. They just help us determine the probability of where the next dart will land. The orbital in an atom is similar to our dartboard analogy. The orbital doesn't tell us where the electron was or will be next, but it does describe the probability that the electron will be at a particular distance and direction from the nucleus.
The atomic theory has come a long way from the time of Democritus, who simply proposed that an indestructible particle existed. Dalton's atomic theory followed more than 2,000 years later as the first atomic theory with any experimental backing, viewing the atom as a solid, indestructible mass. Since Dalton's time, scientists have been filling in the details as more information through experimentation has been learned. J.J. Thomson's work with the cathode ray tube led to the first discovery of subatomic particles, which shattered Dalton's indivisible atom. Thomson proposed the plum pudding model of the atom, which continued to describe the atom as a solid mass with negatively charged electrons stuck into a lump of positively charged protons. The discovery of these subatomic particles was soon followed by Rutherford's gold foil experiment and the hypothesis that the atom wasn't a solid mass at all, but was composed of a dense, positively charged core surrounded by negatively charged electrons in mostly empty space. Very soon, Bohr, a student of Rutherford's, refined Rutherford's model. In Bohr's model, the electrons move around the dense, positively charged core in fixed circular paths. He explained that the energy of the electron in a particular path or orbit is quantized. In our next lesson, you will learn that the view we now hold is that of probabilities in electron clouds. In other words, our modern model of the atom is concerned with the likelihood or probability of finding an electron in a certain position. Today's definition of an orbital will be studied much more closely.
Wow. You talk about deep, and we're not even finished with electrons. Well, that's enough for today. Let's try our chemistry quiz, and then you'll have a chance to practice using the wave equation. Write the answers to each of the questions in your notes. Your local teacher will go over the answers with you after I say goodbye.
Goodbye.
Cumulative review question number 1. An atom is neutral because it has the same number of protons as it has A, electrons, B, neutrons, C, neither. An atom isn't neutral.
Number 2, a solid has a blank shape and a blank volume. A, definite, definite. B, definite, indefinite. C, indefinite, definite. D, indefinite, indefinite.
What is it, Cindy?
D, indefinite. Indefinite. Now, let's review today's material. Question number 1. An excited atom, A, has a date for the prom. B, is the same as an atom in the ground state. C, has absorbed a photon of energy. D, very stable.
Question number 2 for our review is, in a flame test, we see color because A, excited electrons give off energy as they return to the ground state. B, the nichrome loop burns when placed in the flame.
No.
C, our eyes perceive an optical illusion. D, the absorption of it. A, except in a flame test, we see color because A, excited electrons give off energy as they return to the ground state. B, the nichrome loop burns when placed in the flame. C, our eyes perceive an optical illusion. D, the absorption of energy from. The flame is seen as color. Now, question number 3. According to Planck's theory, light, A, behaves as a wave, B, behaves as a particle, C, is negatively charged, D, has a dual nature. Question number 4 asks, in the formula C equals lambda times F, what does C represent? A, the wavelength, B, the frequency of the wave, C, the energy of the wave, or D, the speed of light.
Our last question in our chemistry quiz today is, the modern view of the atom has come a long way from that of a solid, indestructible sphere. A, true. B, false. I hope you did well.
All right, without talking, when you're done, pass out the paper to the front. Without talking. That means sans talking. That means don't talk.
We got the one. We didn't share the answer.
All right, here you go.
We didn't share the answer. It's okay. They're probably wrong.
As soon as I get these graded, I will hand these back to you so you'll have them to finish the worksheet. I'm way behind time. Let's see if I can get these done.
Way behind
before
time.
minutes.
4 minutes. Look at the board. That's just about to end. We're gonna go to lunch.
I thought you started doing lunch.
Me too.
Because I feel like you took it. Okay.
Oh, did you hear my brain just cracked?
I keep it in my pocket. So
Those are your business cards.
Wait,
Look
I
at
should glue
this.
them to my business card.
Cindy,
Yeah.
Kelly,
57.
What'd you get wrong?
Kevin,
34.
I got 2 wrong. How did you get wrong?
2.
2? Oh, me too.
I got the same ones wrong.
Really?
Yeah.
This one was D.
Why didn't you put D?
Huh?
Why didn't you put D?
No C.
No, it was D. What? Wait, that's what we put.
I put 8.
Number 2?
Then I put D.
We put B.
Patrick,
I see that. I'll go to the teacher. Yeah. What if he got it wrong too? That's just gonna take a point. Let me check someone else's. Can you check what they got for 2?
A.
Is that wrong?
Right. She didn't say it.
Oh well, that's gonna take you a point.
Wait. How did you get it wrong? I thought you were smart.
It's cause like I knew the answer, but we missed what were the options? Like which one it was. We missed on which one was on.
You paused it.
Yeah, but like by the time we found out the answer, she skipped it, so I didn't know what it was.
No, that's just a quiz.
Are you guys ready for lunch? Yeah. We're gonna chomp some whatever's for lunch. How do you chomp? How do you check the lunch menu?
You go to I don't know.
I don't know. I'm
On the
asking.
daily bulletin.
Where do you find that? Oh, I'm Power School.
Yeah, I'm good. Yeah.
That's what I said.
Oh.
Oh, okay. Alright. Look at my grades. They're so bad.
You're better than mine.
Obviously.
Oh wow.
Y'all say it's easier. I gotta take it after school.